is my layout. I would first present what lasers are, how they work, different types of lasers, and some latest technologies involving lasers. Then I would discuss some performance parameters. And at last, I would like to present my point of view about Islamization. So, what a laser basically is, this laser, it is actually an acronym for light amplification by stimulated emission of radiation. Uh, I'm just explaining the full form. That is light amplification by stimulated emission of radiation. I'll describe every term in detail in near future, inshallah. So this laser, it is actually a descendant of maser. Both laser and maser are based on the phenomena of stimulated emission, which was postulated by Einstein in 1910s. So what is the difference between laser and maser is just that laser amplifies light and maser amplifies microwave. Only the difference in wavelengths that are amplified. But both are using stimulated emission. I would also explain what stimulated emission is in detail. So how a laser basically works is, we know we have an atom. In an atom, we have the nucleus and energy levels. Okay, so we have an electron in the ground energy ground state, which is not excited. So what if, for example, we have the energy difference between this ground state and this one is the excited state? We have some energy difference between these two. Let that, for an example, be 3 energy units. So what happens is, this a light photon comes, but it should not be a random light photon. It should be of the exact same difference. That is these 3 energy units. It needs to interact with this electron, which is at the ground level. And after interacting with this electron, which was at the ground level, this electron absorbs energy from this photon and it is transmitted to the higher excited energy state. And this process is called stimulated absorption. It is absorption because the electron has absorbed the energy from the photon, and stimulated absorption. This process is called stimulated absorption. Next, when this electron is at the higher excited energy state, it will not stay there for a much longer time, because it is the basic law of nature that we like to be in energy on a low energy level. So this electron, which was there at the higher energy level, after staying there for a few nanoseconds, it falls back into the ground energy state. Okay, and if it falls back into this ground energy state by itself, without the interference of any external force, then this process will be called as spontaneous emission. It is because while this electron is coming from higher energy level to lower energy level, it will emit a photon, and this photon will be exactly equal to this energy difference, which, for example, I told you, let it be 3 energy units. So this is called spontaneous emission. Now, if while this electron is at the excited energy level, if a photon comes and interacts with this electron, while this is at the excited energy level, then this photon is pushed down to the lower energy level. But this time it is not spontaneous, it is because of the interference of this external photon, which has but again, it should not be a random photon, it should be a photon with this specific energy between the 2 levels. So when this photon interacts with this electron here, this electron is then pushed down to the ground energy level, and while it goes to the ground state, it emits another photon. So we have now 2 photons, one which was incident on this electron and the other one which is emitted after this electron goes from the higher state to the lower state. Now we have these 2 photons, and this is called stimulated emission, because here we have some stimulus. For this electron to move into the ground state, we are having some stimulus. That is, this photon is acting as a stimulus for the electron to move into the ground state. Earlier in spontaneous emission, we had no stimulus. This electron by itself came into the ground state. But now, if we have a stimulus, then this is called stimulated emission. So what happens is now these two photons, one which was incident on the electron and the other which is released after the electron goes from higher to lower energy state. These two photons, they have the same energy, direction, and phase. Okay, they have same energy, direction, and phase. So what is the difference between spontaneous emission and stimulated emission is that in spontaneous emission, the one in which we do not have any incident photons, but the electron itself comes down by itself. So this type of light produced by spontaneous emission is random, and it is not very coherent. For example, in an LED, it is in every direction. But in stimulated emission, the emission which occurred due to the incident photon, this type of emission, it is very coherent. Light is, it is a very strong, it is a very crisp beam of light. It is not in every direction. It is a strong beam of light in stimulated emission, as we see in lasers. Okay, so I've already explained this SE terms like stimulated emission. Now comes the part where I'll explain this L and A. What do they signify? L and A, light amplification. So what happens, what a laser basically looks like, we have a cavity, and inside this cavity we have a gain medium. This gain medium is nothing but it is the substance whose atoms we need to excite from lower states to higher states. It is that medium whose atoms we need to excite. So this gain medium, it can be solid, liquid, or gaseous, and accordingly we can have solid lasers, liquid lasers, or gaseous lasers. Sorry. So on both the ends of this cavity, we have two mirrors. One mirror is with 100% reflectivity, and the other one is with a reflectivity less than 100%. That I will also explain why this has to have a reflectivity less than 100%. Okay. So what we do is we have atoms inside this cavity. We need to excite these atoms. We need stimulated emission to occur. For that, we need the atoms to interact with photons. We need photons to impart energy into the atoms so that they can go into the higher energy state. So where do we get these photons from? We place a light source. External lighting is used, and this is called optical pumping. We can have other types of pumpings also, but here I would explain optical pumping. So what happens? We have an external source, external light source incident on the gain medium, so that it emits the necessary photons that will push the electrons from ground state to the upper excited state. When this happens, that most of the electrons are shifted from the ground state to the excited state. Most of the electrons are shifted from the ground state to the excited state. This phenomena is called as population inversion. So when an electron is now shifted into an excited state, it stays there for a very less time, for a very brief time, for a few nanoseconds. But for this population inversion to be effective, I mean, for this, we need this electron to stay at the excited state for a little longer time. So for this, we use metastable states. Metastable states are also excited states, but they have energy very slightly less than the excited states.
You know, you already taken 10 minutes. You know that, right?
Okay, ma'am. So because of this, because of these metastable states, what happens is that the electron now can stay at the excited state for a little longer, from nanoseconds to milliseconds. Now, electron can stay at the excited state for some milliseconds, which is a huge difference as far as the atomic levels are concerned. So what happens is, now we have this excited state. So now we have an electron at the ground state. A photon interacts with this electron, and it is shifted to the excited state. Now, it is at the excited state for few nanoseconds. From there, it falls into the metastable state, which is also an excited state. Staying at this metastable state also means that it is still at the excited state. That means it will be at the excited state for a little longer. So while going from the higher excited state to this metastable state, for example, this electron, it has lost some energy. Okay, if it had the energy difference between ground and higher excited state was 3 units, while coming back to the metastable state, for example, it lost a little amount of energy, 0.1 units of energy. Now, what happens is that this is a radiation-less transition. We know that when electron falls from higher energy level to lower energy level, it will radiate a photon. But since this metastable state is also an excited state, when an electron falls from the higher state to this metastable state, it loses some energy, although it loses some energy, but it will not radiate any photon. So what happens now? This electron is at the metastable state. Now, the only difference is that it has lost some energy. Okay, so now a photon will come with the required energy of 2.9 units, and it will interact with this electron at the metastable state, and this electron will now fall into the ground energy level and emit another photon with the same 2.9 units of energy. So this is the stimulated absorption with the help of a metastable state. With energy level diagram, I would like to explain this. So what happens is that we have here electrons at the ground state. Photons interact with these electrons, and they are shifted here to E3 level, to the higher energy state. Okay, so when they are at this higher energy state, E3 state, now for emission of a photon, they need to fall back into E1. But now we have used this E2 state. E2 is a metastable state. So they will first fall back into the metastable state. The only sole purpose of this metastable state is that so that electrons are at a higher energy level for a little longer time. But it will be a radiation-less transmission. So when the electrons are now at this metastable state, a photon will interact with, if a photon will interact with the electrons, they will shift to the ground state and emit another photon. This is called stimulated emission, like here. In the ground state, the photon comes and interacts with this electron, and the electron goes to the higher excited state. Now, if from the excited state, the electron comes down by itself without any external photon, this is called spontaneous emission. But if a photon is incident and then this excited electron comes down to the ground state, this is called stimulated emission, because it will emit another photon. There will be 2 coherent photons now. So laser light, it is basically monochromatic light. It depends on the medium, what type of medium we are using. So how this now when these pairs are created due to the stimulated emission, these photonic pairs are created. Now they amplify themselves. What happens is that they, in this gain medium, they move back and forth. They move back and forth and interact with other electrons which are at the excited state, and they amplify themselves. A time comes when this beam, it becomes so strong that it can't be reflected by this second mirror, which had reflectivity less than 100%. It can't reflect it back, so it will let it pass through, and we get a strong laser beam. So we have different types of lasers, like solid state lasers. If in the gain medium we have a solid, then it's a solid state laser. For example, ruby lasers. We have gas lasers if we have a gas medium, and semiconductor lasers if we have a semiconductor medium, and liquid lasers. I have also given some examples here. Now we also have lasers on the basis of pumping. As I explained, optical pumping, because of light, the electrons
we are only interested on semiconductor laser. We are not interested in any other lasers, so skip the rest.
Okay, ma'am. So this pumping can be of different types, like for example, optical pumping or electrical discharge pumping. We can have electrical discharge passing through the medium, which can cause excitation, or also chemical lasers. So now latest technologies in this laser field is that researchers in the Fudan University in Shanghai, they have been recently successful in developing an all-silicon laser. So why we do not have till date an all silicon laser. What prevented us from having an all silicon laser is that silicon has a very low optical gain. So what these researchers have done, they have increased the density of silicon nanocrystals. By increasing the density of a silicon nanocrystals, they have been successful in increasing their optical gain increasing the optical gain of a silicon material. So now we can use silicon in lasers because now we can have high optical gains with the help of only silicon use. This has been a breakthrough because silicon is extremely cheap and abundant. And next thing, we are using group 3-4 semiconductors, so we can have sometimes lattice mismatch problems. But if we are successful in developing an all silicon laser, lattice mismatch will not be a problem. So next thing is that researchers from MIT and Harvard University have been successful in developing a holmium doped monolithically integrated holmium laser. So why is this important is that they have been successful in making this laser using the conventional CMOS fabrication technique. They don't need any other fancy techniques, but it can be produced with the conventional CMOS technique, which will make this laser extremely cheap. So performance parameters of a laser.
Okay,
we have, for example,
you are out of time, so I give 5 minutes to finish everything in 5 minutes.
Okay, ma'am. A few performance parameters I would like to explain. If I have we have laser output and its output power. It depends on the threshold current. It depends on current on which we need to bias the laser diode. And if the bias current is below this threshold, so optical power will not be it will be almost zero. This threshold current needs to cross this threshold so that we have the output power which will be directly proportional to the input power. We will get output power only when the bias current has crossed the threshold value. Next thing is beam divergence. It is basically what angular measure of increase in the beam diameter. How this beam diameter increases, this is called the beam divergence. So for a good laser, we should have a small divergence. It should be a very crisp light. It should not divert a lot. Next thing is lasing threshold. So we know we can have both the phenomena, spontaneous emission and stimulated emission. Spontaneous is when there is no incident photon that can cause the electron to come down, and stimulated is when there is an incident photon. So for lasing action to happen, we need stimulated emission. So when the input power is below this threshold value, we will only have spontaneous emission. We need the pump to be at a certain level so that we have stimulated emission, so that we have necessary photons that push the electrons to the ground state, and we have a stimulated emission phenomena happening. Next thing is slope efficiency. It is a graph between the output power and the input power. So we need after the threshold, this needs to be linear, and higher the slope, better is the laser. We need the slope to be higher. Here also I have explained how the slope needs to be higher. Here slope is 0, so we'll say slope efficiency will be 0. These are, you can have a look on these parameters I have given in details. 1 second. So about Islamization, I would like to say that we know that today we in the world we have people suffering from deadly diseases like cancer. So lasers are not only used to diagnose but also to cure these diseases. From complex eye surgeries to mammographies to curing cancer, this laser can be used in treating deadly diseases. From this, I conclude that even if Allah has put us in some difficult situation, but He has bestowed us with enough capability to fight and find the solutions. Like, for example, these lasers have helped us. Allah only wants us to dig deep and look for the solutions. Even if He has put us in some difficult situation, He has given us the capability to look for the solutions. Second thing, which I concluded, I don't know if it is appropriate, but I would like to say that we know that tattooing is haram in Islam. It is a sin. But if some brother or sister by mistake indulges in this sin, lasers have given him a chance to repent before Allah. With the help of ruby lasers, he can get this tattoo removed and repent before Allah and ask for forgiveness. So that was all from my side. Any questions are welcome. Thank you.
Okay, thank you very much, Sister Tamana.
Thank you.
I cannot write here. So open for questions. Question from the floor. You better ask question. I will not cover in the class. And suddenly in the final exam, 60%.
Any questions?
I think I would need to rewatch that a few times to understand and
Yeah,
ask questions.
because the time is limited, I think I need to explain stimulated and this absorption and emission in detail, but I'm really sorry. That is why I have put in detail. You can go through the slides if you don't understand.
I need question now. If you don't ask question, I will deduct marks from your presentation. So at least 2 questions each.
Anything you want me to repeat or any confusions you have?
Yeah, she said.
So the most distinct difference between spontaneous and stimulated is the metastable state, right?
No, between stimulated absorption, emission and spontaneous emission, the basic and the most important difference is that in spontaneous, we don't have the electron, we don't have the incident photon. See, like here. The electron was at the excited state and it has come down by its own. Nothing has interacted with it has come down on its own. This is spontaneous emission. But in stimulated emission, this electron comes down only when when a photon is incident on it. A photon is incident on it and it pushes the electron down. So this is the basic difference. Metastable states are used later on to increase the duration of the electron at the high state. So basic difference between spontaneous and stimulated is that in spontaneous, no incident photon is present. The electron comes down on its own. But in stimulated, a photon interacts with the electron and then it comes down.
Okay, more question. We have like 8 minutes before you will ask us to move out soon or rest. Okay, another question. We'll go through one round of question. Later, Alam will present, and there'll be another round of question, and there'll be another third round to ask both of them. So you have ample of time to learn laser. Now you have 2 teachers here. Okay, who's next?
Can you first share the slides first? I need to organize the thoughts in my head.
Okay.
You can share it in the WhatsApp.
I'll share after the class.
Okay. So during the presentation you understand everything? Iman? That's why no question.
Or it can be.
No, because I don't understand much. That's why I don't have questions. I don't know.
So you don't understand anything when she presented? Iman?
I did catch a few things, but it feels easy in my head.
I think from 100%, maybe around 30 to 40% understand.
So that's why you should have like 60% of question. That's the problem when you don't understand, you don't have question. That's very as if you are not listening.
Actually, I have another question. So basically, the laser, when we need to create laser, we need another light source to have
like this. Not necessarily a light source, but we need some pumping. It can be a light source. This is called optical pumping.
We are talking about semiconductor, Tamana.
Yes, ma'am. Yes, ma'am. In semiconductor lasers, we can have any sort of. We need to have pumping. We need the electrons to go to the higher energy state. 1 minute. A higher energy state. It can be any sort of pumping.
In semiconductor, semiconductor laser, what kind of pumping do you?
Yeah, optical pumping is mostly used.
In semiconductor laser?
Yes, ma'am.
Can you use like electron pumping?
Yeah.
No, your answer is not right.
Let me slide under forward wise.
What's Iman?
Huh?
I mean, no, I was asking if it mainly uses optical pumping, which you say isn't right. Can you use electron pumping or something else? If it's
Electron pumping is mostly used in yeah, helium neon. It is not a semiconductor laser, but helium neon lasers are gaseous lasers. In those we use electrical pumping,
Okay,
not in
So this
semiconductor.
I disagree with that. I don't think it's right. Okay. But I will wrap up the things that which are wrong after Alam's presentation. Then please remind me to go back to the pumping. Okay. Then
Okay.
I will ask more questions. Then you will understand more.
Okay.
So I think let's have a break of 5 minutes and let's come back. Listen to Alam, and then all of you need to ask questions. Tamana ask
Okay.
question to Alam. Is Alam there? I don't know. But are you around, Alam? Is still around? Cannot see.
he says in the WhatsApp the reception is very bad.
Allah, how he's going to present. Okay, so then after that all of you ask question, then I will ask question. Then I
Okay.
will correct things which are not right. And but the
Okay.
one biggest thing I kept on saying, which is you, I don't understand why didn't do this. I told you, right, the heart of all presentation should be on the energy diagram of the PN junction. There's no PN junction diagram here.
Ma'am, energy diagram. I have energy
No
diagram.
energy diagram of a PN junction. This is just an energy diagram of a material. It's not a PN junction.
Oh.
It's not a device. This is just a material. PN junction is the one that we went through, right? You have PUN, you have
Yeah.
and that's the one that you're supposed to explain.
Okay.
But let's hear from Alam first.
Okay, ma'am.
Okay, so let's have a break of 5 minutes, inshallah. Okay,
Okay, ma'am.
Assalamualaikum warahmatullahi wabarakatuh.
Assalamu alaikum.
Okay, go on.
Right. So this is LED stands for light emitting diode. It works in the same way as a normal diode does, essentially. But due to its materials and how it's made, it's able to emit light. Okay. So the characteristics of LED compared to other conventional lighting sources is that it has a low power consumption compared to normal lights from incandescent lights or fluorescent lights, right? And you can make LEDs into really small, really compact sizes. So you can do it for a variety of uses, such as for small 7-segment indicators and stuff. And also you can do it for lamps if you just bunch them up together. They're generally robust. They don't use any type of volatile gases. They're compact and they saturated in color. So this is important since the color made by LEDs, they're only narrow to one specific color. So they're really saturated like the lasers, right? You cannot, it's hard to have a white LED if you just use the semiconductors by themselves, right? So it's hard to have white LEDs, but people have made it. I'll talk about it later. Also, one of the other I think important characteristic is that it can switch quickly between on and off, and you can modulate the voltage and stuff. We'll see one of the applications later, right? So this is an LED. So this is the physical representation of the LED. This is the positive terminal, the anode, and the negative terminal, the cathode, right? And the anode is connected to the P region, cathode is connected to the N region, so it's positively biased. So there's an active region where the recombination occurs, and when the recombination occurs, light is emitted from the LED. Right. The substrate is used to regulate the temperature and also be reflective, because some of the light here will be reflected downwards. So the substrate serves to reflect it away from the LED. Right. And the case is made from epoxy resin, a kind of plastic to protect it from the environment. Right. So this is the I would say simplified version of the process that occurs. So you have the electric field from the voltage here supplying to the semiconductor diode, the LED, and from there the free electrons combine with the free holes uh, to to make them bound. And what happens is the energy resulting from that is irradiated to outside of the LED. It could be either mainly it's light, but it could also be heat. We'll see the difference between an LED and a diode later. So this is called the process of electroluminescence. We changed electrical power into light energy. Right. This is the direct indirect band semiconductors. Right. We've talked about this before in class. Madam talked about this before in class, but essentially the direct band gap, the band gap is the conduction band is directly above the valence band, and the indirect band gap, the peak of the valence band is offset. It's that it's in a different phase, I think. So the peak of the conduction band and the valence band is not the same. So what happens here is in here, when you apply voltage across, the electrons from the conduction band bond with the holes in the valence band, right? And this will irradiate photons, which is light. But what happens in an indirect band gap is that the electrons from the conduction band needs to travel further to go to the valence band, right? And to have this like to travel like this, you would need phonons, which is heat. So heat is generated to cause the electrons to transfer from the conduction band to the valence band. In this case, only electricity, but this produces phonon as well. Some photon may be produced, but that's due to conservation of energy mostly. So usually indirect band gaps are group 4 semiconductors, silicon, what else? Germanium, but direct band gaps are 3-5 semiconductors, right? So this is the light spectrum. We'll see the light spectrum because what happens in the indirect band gap is that once the electron uses up the heat to transfer to the valence band, the photons lose energy when they come out. So when they lose energy, they get closer towards infrared and become non-visible light. So this the visible light is mainly produced by this group 4 semiconductors, the direct band gap semiconductors, which is besides group 4. So light is visibly different because of its wavelength. Since the speed of light is constant, the frequency is inversely proportional to the wavelength. Right? So this has a higher frequency, this has a lower frequency, this has a longer wavelength, shorter wavelength. And the light generated by LEDs correspond to the respective band gap. I'll explain this later. This is because different materials generate different wavelengths of light when recombination occurs. So when you have different types of LEDs that emit different kinds of light, they basically use different materials to make that semiconductors, right? Sorry, that was my mistake. Let's see. This is the band gap. This is not band gap. This is the explanation of what I explained here. So this is the energy band. Eg is band gap energy, and which is equals to Planck constant and frequency. So you can see that the energy is proportional to the frequency of the light emitted, right? Since light is constant, so frequency is inversely proportional to lambda, which is the wavelength of the wave, right? So essentially what happens is, this is just to show that if you have a higher frequency of waves emitted, it will have a higher band gap energy. So based on this graph here that we were introduced to in our first few classes here, there are, you can see that band gap energy, as it increases, it goes towards the ultraviolet, and if it decreases, it goes towards the infrared. This is similar to here. When the frequency increases, it goes to ultraviolet. When it's less, it goes to infrared. So this is just to show which LED color are for which semiconductors. These are usually for 3 and 5 and 26. For group 4 semiconductors, they are generally used as diodes and not used for LEDs. Right? I think this is incomplete. So, but generally for LEDs, there's luminescence, which is the intensity of light corresponding to the wavelength, right? So this has around a peak of 500, 550, which is around blue. So the light is strongest at blue, but it doesn't mean that it doesn't have other wavelengths, but it's primarily blue. So that's why when we see the LED, it looks saturated in blue, right? So this is the current and applied voltage. The current is supposed to increase exponentially as you increase the voltage here, right? So I'm talking about the current technology now. This is I wouldn't say this is recent technology, but this is one of the most important technology regarding LEDs, right? So recently, 20 years ago, there was a discovery of blue LEDs from gallium nitride, or indium gallium nitride semiconductors, right? So what this allows is the production of white LEDs, right? But remember, since white LEDs are not possible, we need to change it a bit to make white LEDs. So beforehand, what we did was we combined the 3 main color spectrums to combine it and generate white light. So you have red LED, green LED, blue LED. So what that means is the color mixing isn't as it's not as varied. It's not, you have peaks here, peaks here, peaks here, but it's not like it's not a what do you call it? It's not a mountain, I would say. But with the invention of blue LEDs, what you have is this white LED, which is made from using the blue LED with phosphor, right? So the phosphor is excited by the blue light generated by the LED, and the phosphor generates yellow light. So once it combines with the blue light, it gets a sort of white light here. So this is the white emission. So you can have different types of phosphor. You can have red phosphor, and the peaks would look it wouldn't look as drastic as this. It would be a bit more. There's bit more peaks here, bit more peaks here. But the using yellow phosphor here would be the cheapest way. Right. This invention is so important. It won the Nobel Prize in Physics in 2014, and even though it was made in the 90s, so it was really important then. So one of the recent researchers in LED applications, which is coincidentally what I'm doing right now, is about visual light communication. It's otherwise known as Li-Fi. Similar to Wi-Fi, you have some sort of source that gives off the waves. So Wi-Fi, you give off radio waves. This gives off light waves, light waves. So you can do it from LED lamps. So what these do is that when you modulate the voltage of the LED, it turns on and off, right? Even though, and you can do it so fast that the human eye cannot differentiate between it being visible or flickering, right? So it doesn't look like it's flickering for human eyes, but for devices that have the capability to read the light getting in, it will notice it will flickering and will convert the flickering to data. So currently it's mostly a one-way communication network, meaning from the light source to the device. But there have been research going into having there have been research going into the LED lamps having the capability to absorb um, the light given off by other devices, which would need primarily two LEDs here. No, two diodes here. One to emit and one to receive light. Right. So on towards Islamization, I am when I studied this topic, I am reminded of this ayat here. So the translation is that Allah is the light of heavens and the earth, right? So Allah is giving here a parable of the importance of light. So it says that the example of his light is like a light within a lamp, and the lamp is the light is all-encompassing. It reaches everywhere, right? Light upon light, nurun ala nur. So I think it's interesting how Allah gives like parables or talks about light in such a way so that you have other ayats that goes like يَخْرُجُكُم مِنَ الظُّلُمَاتِ إِلَى النُّورِ to take you from darkness into light. So of course, in that case, light would mean hidayah, but it would also mean that it's also interesting how Allah does this comparisons, right? So and in this like topic, we can see that light itself has a lot of uses, and even for communication. And yeah, I think that's it for me. Thank you.
Okay, thank you, Iman, for the presentation. And open the floor for question.
Any questions? I mean, anything not clear? Because I think this is a really basic presentation. I hope you understand.
Question, yes, Tawana.
Yes, ma'am. Can we use any semiconductors to make an LED? What type of?
You can do it's mainly direct bandgap semiconductors. It's mainly direct bandgap semiconductors. While you can use photons here, the loss of energy from photons make it so that, I mean, I don't think I understand this topic that much to answer that question. But from what I can and from what I can guess here is that once you generate phonons from this transfer of electrons, right, the energy from the photons become less, right? And since it doesn't necessarily produce photons as in itself, that means it's really hard to produce photons when you have an indirect bandgap semiconductor like silicon or germanium. But indirect bandgap, such as gallium nitride, it's easier. So we mainly use gallium nitride. Indirect band gap.
That means we can use any semiconductor which has band gap in visible range.
Yes. I haven't seen anything, any LEDs are using light outside of the visible range. So I'm not really sure how those would work.
Yeah.
It can be as long as it's I'm mute, sorry. Can you hear me now?
Yes, sir.
As long as it's the direct band gap material, it will give out light, and it can be visible or not non-visible light. You can buy what do you call it, infrared LED. Infrared LED is not visible.
Infrared.
Yeah, gallium arsenide is infrared LED. You cannot see the light. So you can see it's slightly beyond the red, right? So gallium arsenide is infrared. It's not visible, but you can still, it's still an LED. So so you can have. Is that what was your question? Is that, I know what your question about. Sorry.
Ma'am, I mean all the whichever semiconductor has a band gap in the visible range, we can use that, or it can be infrared also. The semiconductor needs to have band gap in the visible range only.
Okay.
First, it needs to be direct, and second, does it need to be visible?
It doesn't need to be visible. I think there's uses for infrared remote controls where they use infrared LEDs to control the TV, right? So in this case, the LEDs the mostly used ones are, or the used ones are direct band gap in any visible light, in any light spectrum, actually. Although I'm not sure what happens in the photon produced here. Oh, I mean.
Ma'am, did you say gallium arsenide is in
your drawing
IR?
is wrong. Wait a second. Your drawing there is wrong. The second one, the indirect, it doesn't give out photon. It gives out phonon.
Okay.
So the photon is wrong. It's supposed to be phonon. That's another question that actually I want to ask you. So because the diagram is wrong. Can you explain? Maybe can you explain this again? What do you understand from the indirect band gap?
So okay, yeah, explain again. So from the indirect band gap, we see the direct band gap. It uses the electricity from the drift current. So the electron goes from the conduction band to the valence band and bounds with a hole. For this, the electrons goes to the valence band. Since it needs to travel a bit further, it needs to use up energy in the form of heat to move the electrons from the conduction band to the valence band. So
I think that's, where did you get that? You read the book?
I read articles and watched a lot of YouTube videos.
Oh, okay, that's good. Watching a lot of YouTube videos. No, the concept of indirect band gap is similar to direct. Basically, you have recombination. Both here we are talking about recombination. So when we have recombination, which is from conduction band to valence band, what does it give out? Okay, so for direct band gap material, because of this is a graph of the energy versus K. K is momentum. Okay, so this is not the normal, we draw the energy band diagram, energy band that we draw normally is distance on the x-axis, but the x-axis is K. K is momentum. So they call it, sometimes they call it EK diagram. So in the energy momentum graph, for direct band gap, the conduction band, the minimum meets the maximum of the valence band. And when this happens, when you have recombination, it can recombine directly and you are not losing any momentum. You don't have to change momentum. The momentum is the same. When momentum is the same, the output is photon. You get light. Okay, you get light with all the characteristic of a light, photon. However, when for indirect band gap material over here, you can see the minimum of the conduction band is not on top of the maximum of the valence band. And when this happens, recombination will also occur because electron wants to go to the lowest possible state, so it will go to the valence band. However, when it recombines, what happens is it needs to change momentum. So what happens? I don't know. You cannot see my. Can you see my cursor? Cannot.
No. It's my cursor.
Okay, so what happens is the electron there, the blue ball there, will go to like directly and then change direction. So it will go direct to the bottom and then change and go to the left. So which means that
Okay.
it will still go to the valence band, that it will change momentum. When momentum change, we will no longer get out. We will longer uh, it will no longer emit photon, but it changed to phonon. So that's why you need to correct this. It's phonon instead of photon. So nothing to do with it's the same recombination process as the direct band gap. However, the output is different. Okay,
Okay.
no question.
So the only difference is it loses the momentum, right?
It changes the momentum. Change.
So,
Loses energy, change momentum.
but if you increase the momentum, because the k is the x-axis, right? So if it loses momentum, what's the difference if it would lose momentum and would gain momentum? For example, if the valence band is on the right.
As long as it will change momentum, the momentum is not the same, then you get phonon, regardless on the right or the left. As long as, because if you look at the direct, it's directly beneath, which means that the momentum is not changing, it's the same momentum. But
Okay.
in order for recombination to occur for indirect, it will change momentum. Anything that change momentum will change the property of the emission from photon to phonon.
Madam, 1 minute.
Huh? Okay,
Less than
so we'll continue the question afterwards. What's the time now?
3:30,
What time we
3:27. We started at 2 and we had a break for 5 minutes, or 3:35 or something.
so we are out of time.